Okay, welcome back. So let's start. You saw how we could find a linear non-Gaussian causal model from data, right? And now let's first of all look at two problems. One is how to deal with the confounders, latent confounder in a very simple way. Later you can see how we can really deal with the confounder in very general situation. Right now, we know confounders, latent confounders can cause a lot of trouble. By the way, when I say confounder, usually I mean latent confounders, right? But in statistics, sometimes you have observed the confounders. Okay, so for this part, let's assume that latent confounders are not related to each other. Okay, this is the so-called canonical representation. Why? Because you can, if A causes B, in principle, you can always write down B as a function of A and independent noise terms, right? And then instead of using B, you can just use independent noise terms, which are independent from A in the latent part. If they are not observable, then you can always use independent things to represent the same distribution. Okay. However, later you will see, tomorrow you are going to see that that's not necessarily the case. Why? Because if you really want to use independent hidden things to explain what you see, the model can be very complex. It's very weird. So that's why we actually can try to recover the causally related latent variables later. For now, let's just stick with this assumption. Specifically, we assume there's a single latent variable. Then you can see what we can recover in the linear non-Gaussian case. For now, let's use the linear non-Gaussian case because we know that if you have only two variables or very few variables in the linear Gaussian case, generally speaking, you cannot recover the latent variables, right? Latent confounders. If you have multiple latent measured variables, it's possible. Remember this example: 1, 2, 3, 4, 3. Right here, they are independent, right? Then we know here you may have circle. Even if you apply FCI, then here there must be. Remember this example: 1 independent from 4, 1 independent from 3, 3 independent from 2. Then we know right here they are latent variables, right? But we have to make use of multiple measured variables. And in specific cases, we can do so. Generally speaking, in the linear Gaussian case, it is quite difficult. However, once again, tomorrow morning, you are going to see that if you have many measured variables under rather mild assumptions, you can really go to the world of the hidden variables and the relations. And you can see how tomorrow morning. Okay, so tomorrow we are going to see how we can go further in those directions. First of all, what's latent confounder? If x1 is missing, suppose this is the true causal DAG. If x1 is missing, is it latent confounder? No, it's not a direct cause of two variables. Okay, cool. Then we can easily skip this. What if x2 is missing? If x2 is missing, is it latent confounder? If x2 is missing, is it latent confounder? Is it missing variable? Is it latent variable or hidden variable? Yes, but because it's not measured. Is it a direct cause of two variables? Is it latent confounder? Yes. However, you want to say no because this guy is also effect of some other variables, right? But still, it's a latent variable. It's a latent confounder. However, you may say, oh, you can have another way to represent the latent variable. You say x1 and x4 influence 3 and 5. So if you ignore this guy, you just have the influence from 4 to 3, and from 4 to 5, and from 1 to 5, and from 1 to 3. Right? You ignore this guy, then the indirect causal influences will become direct. Right? But on top of that, you also have the noise term in x2 as a direct common cause of x3 and x5. Right? Because x2 had two parts. One is the contribution from other measured causes, the other is noise. Right? The noise part is still hidden variable, it's a latent confounder. I mean, you can convert this representation to another one where the latent variable, noise term in x2, is independent from other causes. Okay. Good. That's not commander. Now we remember this is very messy, but the message is very clear. Even if you have only 2 measured variables, but 3 or even more hidden variables, under some conditions, you can estimate a matrix or columns of a matrix, as you saw from this theorem and this illustration. Remember this. If you see if you just see this scatter plot, you know right here, this is you can estimate the column. You can immediately estimate the mixed matrix without any difficulty, right? Even by visual inspection, you can do so. For machines, they can do so. If they are very non-Gaussian, it's easier. Otherwise, it might be pretty difficult. Maybe you need a lot of data points, but that's not a theoretical problem. Okay, so you can estimate the contribution or the mixed matrix from multiple or more independent sources in the non-Gaussian case. Good. Why am I talking about this case? It's because if you have latent confounders, clearly you are going to have more independent variables than what you can observe, right? Okay, let's look at this very simple example. Again, 2 variable case. You have x1 and x2 with the latent compounder z. You measure the values of x1 and x2. In this case, in the linear non-Gaussian case, what can we recover? Given this causal model, x1 and x2 are basic linear combinations of 3 independent things, including z, E1, and E2. Right? Previously, without this guy, x1 and x2 will be linear combinations without z. x1 and x2 are linear combinations of E1 and E2, where E1 is identical to x1. Right? That's a previous setting without the latent confounders. Now we just have more independent variables because they are latent confounders on top of the regular causal influences among the measured variables. Good. So traditionally, especially some time ago, people just tried to identify the causal relations among the measured variables, even if they are latent confounders. So they don't care very much about influence from Z, but they try to identify the causal relation among the measured variables. Why? Because very oftentimes you want to change some of the measured variables and see the consequence. That's why. But now, especially in causal representation learning, you care about latent variables as well, because they are meaningful, right? You want to reconstruct them for some purpose, for some specific reasons. Okay, so this is mixing procedure. Here basically says that x1 is influenced by x1 is influenced by E1. Yeah, that's the case, and also influenced by Z, as you can see from here, with parameter with coefficients A1. X2 is influenced by E1 with coefficients A3 and E2 with coefficient 1. Now is additive, right? And from Z, we have 2 paths, right? So the total causal influence from Z to X2 would be A2 plus A1, A3, as you can see from here. This is the whole mixing procedure, right? Now we are getting only the data. Can we recover all those things? That's the question you want to answer, because if you can recover A1, A2, A3, you recover the whole causal picture involving the latent variable. Is that right? Okay. Because the previous theorem, right, you just saw the illustration here, we can estimate those columns relatively uniquely if you ignore the permutation indeterminacy. Good. Now you can recover those things. Okay, now suppose you recover those 3 columns up to permutation and rescaling factors, right? What can you say? You are given this one. What can you say? First of all, are you sure that x1 causes x2? First of all, we know that they are latent confounders, right? We know there is no kind of a linear model so that the noise term in x1 or x2, right? such that it's independent from the hypothetical cause. We know there is no such a case because we have one more latent variable. Remember, in the linear non-Gaussian case, as long as the two things receive the contribution from the same non-Gaussian variable, they are not going to be independent, right? As long as they receive contribution from the same non-Gaussian component, they will be dependent. Okay, so now you estimate this guy. Oh, if you estimate it, I know, oh, there must be a latent compounder. First question, do you know x1 causes x2? Yes, right? Why? See here, I have one column where this guy is 0. That means something can influence x2, but not x1. If x2 causes x1, that's not possible. Because if something influences x2 and x2 influences x1, then that thing will also influence x1. Right? So we know x1 causes x2. At the same time, we know there is a causal relationship in between right here. And okay, now first of all, we can see the causal direction. It's going from x1 to x2. Second question, do you think we can determine the coefficients A1, A2, A3? Yes or no?
I mean, all of them?
All of them, or some of them, doesn't matter, right? You just want to share, you see what you can
Here
discover.
it seems some of them you can, but
Which ones?
A3, I think.
You can determine A3? How?
I mean, this thing is we can estimate, right?
Yes.
So I mean, we know the position of A3. But
Mm-hmm.
we can just estimate the matrix and see.
Okay, you know the location of A3, that's why you see the value of A3. Do you agree?
One doesn't have a thing.
X1, no, X1 causes X2. Yeah, because here you can see, or X2 does not cause X1. I'm very sure about it. Why? Because if X2 causes X1 right here, then here you can see X2 receive the influence from something, but the same thing right there does not influence X1. But if 2 influence X1, that's not possible. If you cause me, then anything that causes you will also cause me. Right? That's why we can see the direction. Now you want to see whether you can identify the parameters. And you care very much about A3. And the gentleman said, yes, you can identify A3. Okay, now the assumption is not true. So you said you know the location of A3. Do you agree? Remember, we can only recover the columns up to scale indeterminacies, right? How can you say this is S3? Can I say this is S3 instead? Can I? I say this is S3. Oh, I say this one divided by A1 as S3. As you can see from here. I can change, I don't care about the factor, right? The scale. Now I can see right here is 1 coefficient. Can I say this column right here, this is the new S3? It's possible. So right here, fortunately, there are only 2 possibilities. You have 2 possible solutions, 2 possible values of S3, as you can see from here. This is the alternative solution. This is the original one. Of course, you can recover this one or this one. Right here, this is the new value of S3. It's a true S3 plus this guy and this coefficient. Okay, so basically, it's still good because there are only 2 possible solutions. You can identify this causal influence in the linear non-Gaussian case. And if you have further background information, then you can just eliminate one of them. It's possible. For instance, if you know that all those influences should have the same sign, for instance, then this one is not possible because here the latent confounder has to influence the 2 variables in different ways, positive, negative, right? So if you have some background information, you can eliminate some of the possible solutions. Okay. In this case, we have 2 possible solutions. Actually, in some cases, we have a unique solution. If you look at this example, by the way, this was given in the second paper. Yeah, this paper we published. Well, it's already 3 years ago. Yes, right here. So you can see in this case, the second one. Oh. Right here, you can see y, right? I can consider this as A, and then I can find the values of A1 and A2, new values of A1 and A2, as you see from here. And they are observationally equivalent, right? So in this case, this latent confounder right here, actually you have a unique solution. I will not really explain why, but basically the condition is the following. If the independent variables right here, independent variables Z, C0, E0, E2, and E2, do not have the same support. And here I define support as the variables that are influenced by the latent variable. Okay, then on that condition, the solution will be unique. And now you can see why in the previous case it's not unique, because E1 and E2 have the same support. Both of them influence X1 and X2. That's why I cannot distinguish between them. But if they have different support, as you can see from here, the solution will be unique. Okay. By the way, some of you are familiar with this graph. In causal inference, identification of causal inference, even if this is latent confounder, you can consider this as a surrogate, and then you can still identify the causal effect under some conditions. Okay. So here you can see basically illustration. I'll try to make sure you can see why. Right here, we have the scatter plot of E1, E2, and Z. They are independent, as you can see from there. They are sparse. That's why you can see we have a kind of line pattern parallel to each of those three axes, right? And then this is scatter plot of X1, X2. If I see this pattern, I can immediately tell you that X1 causes X2, but not the other way around. Why? At line, you see this kind of pattern, you know, oh, there's something that influences X2, but not X1. Clearly, right? You can see the direction. Here you can see some simulation results. Basically, it's just what I just talked about. This is the true one, and then you can have the true one, or more almost the true one, even if you have latent confounder, or you can have alternative one. That's it. So you can really solve the problem if the independent variables are non-Gaussian. Of course, there's a problem here. In theory, it's beautiful, but in practice, doing ICA independent confounder analysis with more independent variables than the measured variables is a problem. Why? Because it's harder. You have, say, only 2 measured variables and the mixtures of, say, 4 independent hidden variables. Then a lot of information is lost in this mixing procedure. So it's really hard to recover the model in practice, right? So you might have local solutions. This problem is known as overcomplete ICA because it's overcomplete. You have only 2 variables and you have so many hidden variables. Equivalently, you can say it's underdetermined ICA because it's not determined, it's underdetermined. You don't have enough information to determine everything, right? So it's overcomplete ICA or underdetermined ICA. In practice, it might be hard. Tomorrow morning, you are going to see how we can avoid doing overcomplete ICA to recover this mixing matrix right here, while you can still recover the locations and the relations among location of latent variables and their causal relations. So tomorrow you are going to see how we can actually make use of some specific combination of the measured variables to look into the hidden world, to really see something about the causal relations. Okay, is that clear? You still want to avoid using overcomplete ICA, although in theory you can do so. Now let's look at cycles. Regarding latent confounders, or this particular way to deal with the latent confounders, is there any question? You saw what you can benefit from the linear non-Gaussian model, right? Because overcomplete ICA model is basically identifiable. If you only care about the mixing matrix A, from there you can try to recover the causal relations among the measured variables as well as the influences from the latent variables. Okay, but very often times you don't have a unique solution. In specific cases, you have. So now cycle is very important. So in this part, I will first give the interpretation of cyclic models, and we will try to relate causal representation with cycles to the underlying causal process. And then I will briefly discuss why this kind of interpretation is so important, because in causal discovery, you just want to analyze whatever kind of data you have, right? And then you try to say, oh, it's causality. It's too good to be true. The data could be very different from, and the data in the data you have, causal information may disappear, right? Compared to the true causal process. How can you make sure that the discovered relations are consistent with the underlying truth? We have to see the connection. And right now, you are going to see this kind of connection in specific situations. Okay, so this is the feedback right here. You can see you can go from X2 back to itself, right? After 2 steps. It's a cycle. And sometimes if you have an immediate cycle, say if you have inference from 2 to 3, back to 2, and then some people say it's a 2 cycle, because, right? That involving 2 variables, the 2 cycle. That's the terminology there. Right here, we have a cycle. What can we do? On the left, you can see the equations, because I can always write down structure equation models. X1 is influenced or is determined by exogenous noise. X2 is determined by X1 and X4 and noise, and so on. Once again, the noise terms will be independent if there's no further latent compounder, right? Noise terms will be independent. Good. This now right here, we have this set of equations. We try to recover those things from data. We only observe the data for X1 to 34. 5, yeah. What can we do? Now, let me ask you a couple questions. First of all, the noise terms are independent. Let's consider even a simpler case. Suppose we have only 2 variables, say X1, 2, X2, 1, 2. Suppose we have a cycle right here. I know that the noise term in X1 and the noise term in X2 are mutually independent, right? Because the noise terms are some kind of real things that you cannot measure. Right here, they are independent. Otherwise, there must be another way for them to be related. In other words, you have another latent compounder for the variables. For now, we assume there is no such a latent compounder. Noise terms are independent. So if you have only 2 variables, then the noise terms in X1 and X2 will be independent, right? Will be independent. So EX1, that's always the case. E1 in X1 is independent from noise term in X2. Good. Now, can I say that the noise term right here, I can say this, suppose this is beta, this is alpha, X2 is a function of X1 plus noise. The function looks nice, right? The inference from X1 and noise. The question is, do you think E2, the noise in X2 is independent from X1? Because do you think E2 and X1 are independent? In the previous case, yes, that's an independent noise condition. Noise should be independent from the parents or derived causes. If you have cycles, as you can see from here, do you think E2 and X1 can be independent? Why?
Because you have cycles.
Why? Yeah. So it's a phenomenon, right? You have to say why they shouldn't be independent. You're totally right. There's a cycle, they are not independent.
Right, X1 in terms of X2 plus X1.
Yeah.
Put back to the.
Yeah. So you are saying I can also write down X1 as a function of X2 and noise. That's not the answer to the why question, right? You're totally right, you can do so because there's a cycle. Then why do you think X1 and E2 are not independent? There's one very small gap. Go ahead. So since, let me just kind of add one more sentence. So that means X1 also receives the influence from E2. E2 is part of X2. X1 is also influenced by X2. So X1 also receives the influence from E2. X1 also receives the influence from E2. That's why they cannot be independent in the non-Gaussian case. Is that right? So now we can see they are not independent. Good. So we cannot use independent condition. That also means that if there is a loop between X1 and X2, then basically you cannot say it's a regular causal model without a cycle. You cannot say X1 causes X2 because in that case, the residual will not be independent from X1. Good. Now let's see whether we can recover this model from data. And then, is that the case? Before that, before estimating the model, let's have an interpretation. Let's start with the underlying true causal process. Here I have two processes, X1 and X2. There's some time delayed causal influence, as you can see from here. For simplicity, suppose it's linear. Then xt is a linear function of xt minus 1, right here, plus noise. If you have time series data generated by this causal process measured in the right way, then you can directly estimate B. This is nothing but vector autoregression model, right? Okay. Right here, you don't care about the cycle. And there's no cycle, X1 to X2 to X2 to X1. Looks like a cycle, but you don't care, right? Because they are different variables. Very good. Yeah, very often times you consider this example. I gave this example before. Price demand. I know this is the case. And then in each of the locations, say different states, I care about what's E, what's the noise term. The noise term is a specific property of the location relative to the whole population. So I consider all states in the states, all states in the United States, right? And then in Texas, you have a specific value for the noise terms, right? That's a specific property. And in California, you have another value for the noise terms. Good. Then if I wait long enough, the process will disappear. So this process will convert it to one value for X1, X2 in Texas, another value in California, another value in New York, and so on.
What is it? So it doesn't change through time.
Oh, that's very good. So here, the noise term, as I just mentioned, the noise term is something specific for a particular scenario. Yeah, it's the same. And you are to the right. Later, you can consider another scenario. Okay. For now, we consider this equilibrium state situation. Suppose you have a new product. At the beginning, clearly the price will change a lot because demand will also change a lot. And then after some time, you see, basically you will reach the equilibrium state. That's what I mean. Because in this case, in the state, the noise term should be relatively stable. Then, okay, now we have convergence of the process. In Texas, you have one value for X1 and one value for X2 upon convergence. In California, I have another one. Now, since the process converges, we can say xt equals xt minus 1. Right? They are equal to each other. Is that right? Then we have this equation. Are you familiar with this equation? X equals B times X plus noise. This is the model we just tried to estimate 3 or 4 hours ago, right? Okay, now good. They are consistent. They have the same B, the same causal adjacency matrix. Is that right? So if you have equilibrium state situation, then you have to consider the values produced by multiple processes in different circumstances, and then you have a distribution because now you can put data together, put the data in California, Texas, Florida, Pennsylvania, New York together. Then you have a data set, and then the data set will follow the data right there will follow this model, where the noise terms are still independent. Okay, this is something you are familiar with. Now, if you can estimate this model from the data, equilibrium state data, equilibrium state data. Can you recover the true causal relations? Can you recover the true causal relations represented by this equation? Yes or no? We know that from such data with ICA-based method, it's possible to recover such a B matrix. Now my question is, given that, can you recover this model? This question looks kind of trivial, right? But still, maybe you can give an answer. And then I will say no. It's something you may say yes, right? Remember, there's one problem here. B here, the diagonal entries of B are usually non-zero. It's a self-influence, self-loop. Clearly, right, for price, current price is also influenced by the previous price. The entry of B right here is non-zero. But in this model, we assume the diagonal entries are zero. That's the only difference. And then you can easily see the correspondence between this B with zero diagonal entries and this B with non-zero diagonal entries. They are very similar. They have the same support. The scale or the value might be slightly different because of the self-loop. But qualitatively speaking, they have the same support. If Bij is non-zero here, it will be non-zero there. If it's zero here, it will also be zero there. That means you can really recover the causal influence information. Although if you really want to recover the causal quantitative information with causal influence in the original process, you may need to go further. For instance, you may want to see how strong the self-influence is or self-loops are. And then once you have such information, you can go from this guy and the additional information regarding self-loops to recover everything here. Okay? Questions? To summarize, qualitatively speaking, good. Even if I have equilibrium state data, I can recover causal relations. I can trust such causal relations. That's cool. That's why, okay, I'll stop because now comes the second case. That's the equilibrium state situation. As you just mentioned, the noise term can change all the time. You may not have the equilibrium state situation, right? Consider another scenario in the stock market. We know that if one changes, the other will change very quickly, right here. We have a number of stocks. If you really go to the causal process, you can see the causal relations, right? Hang Seng Bank will influence HSBC because basically it's a part of HSBC, since HSBC holds 60% of Hang Seng, right? So you have the causal influence. But this causal influence will take place very quickly, within 1 minute. Good. However, very often times we want to use low resolution data, like daily return. What's daily return? Daily return is nothing but the aggregation or total sum of the short-term returns. Is that right? If you use the log return is the log closing price minus log the price at the very beginning, right? And this clearly, this total difference is the total sum of the small differences, right? Okay, if that's the case, now you just have this way to generate data from the true causal process. This is true causal process. And then if L, the aggregation factor is big enough, then you can see right here, those two terms will be identical to each other because they differ only in one small step. If L is big enough, those two terms will be identical. Right? Let me draw something, you see why. So, oh, I already forgot. So you have x1, t to influence x2, t plus 1, and so on. After one time delay, you have such a thing, right? And now if you take the average or aggregation right here, Now you can see, I can ignore this part. This is the only thing for them to be, only reason for them to be unaligned. This is the difference. But if this window is long enough, then this part and this part will be very small. I can ignore that part. Then the two terms will be identical, right? Okay, if that's the case, once again, we have this model. This is what I can measure. This is the average or aggregation. So xt equals b times xt, the same thing plus noise. If you take the sum of the noise terms, given that they are independent all the time, after you take the sum, they are still independent. So once again, we have this model. That's why we can still make sense of the causal relation you discover from the daily returns of the stocks. Right? So this is the aggregation or temporally aggregated data. And in this case, you can see you don't have to assume that right here we have a fixed value for noise term. Noise can always change, but you take the average. And eventually you still have the stock allocation model, as you can see from here. And similarly here, you can recover the qualitative information, but you cannot recover the self-loop information. You know, the resolution of the data is so low, you have to sacrifice something. Here, you just happen to lose the information of the self loops. Now, how can we estimate this guy? How can we estimate model? If the model is acyclic, you already know how to do it. In the morning, right? You saw how we could estimate. Yeah, in the morning, how you saw how we could really estimate the linear Gaussian acyclic model. Now, there's no difference between cyclic model and acyclic model. Right here, if you really have the causal process, you don't care, right? It's the same thing. 1 infinite 2, 2 infinite 1, it's same thing. Now, we also want to have a unified view, even if you don't have time information, meaning that even if you have only the data collected in the equilibrium state or aggregated data, we still want to recover the causal graph, no matter it's acyclic or cyclic. We have a unified way to do so. How? Here you see examples. Okay, now we have very simple loop. x1 to x2 back to x1 right here. And this is the causal relationship. x2 influence x1 with b parameter, and x1 influence 2 with coefficient a, right? Now, from the distribution of x1, x2, we want to recover this guy. Let's go the same way. X, and then this is the, I have data x, I want to apply, suppose I apply ICA, this is the demix matrix or promoted and rescaled version of the demix matrix. And then here, if I do the previous permutation and rescaling thing, the operation to derive the B matrix, I can have another solution. This is one solution, and here I can have another solution. Because now there is more than one way for you to permute the matrix so that the diagonal entries are non-zero. Right here, this is fine. If you switch them, still the diagonal entries are non-zero. Right? So that's the only thing you don't like. That means if you have cycles, you can still do the same thing. You can still produce an independent component. Why can we do so? Because even if there are cycles, we assume the noise terms are independent, although the noise term is not independent from the cause, because now the cause is also effect, right? They share some information. However, we can still do a linear transformation to produce independent components, and we can still find a solution, although the solution is not unique. There are only, in this case, there are only two possible solutions. Okay. However, would you prefer one over the other? In reality, the system is stable. AB, basically, the product of AB should be smaller than 1 in absolute value, right? Otherwise, the system will explode, right? So if right here in the true model, if the absolute value of AB times B is smaller than 1, what will happen to the alternative solution? In the alternative solution, the coefficients are 1 over A and 1 over B. That system is crazy because the self-influence, right, from H1 back to itself would be 1 over A times 1 over B. So in absolute value is bigger than 1. That one is not stable, right? So you can still prefer the one with a smaller loop, self loop. Specifically, if say B is 0 here, then this is acyclic if B is 0, right? And or if B is very small, clearly you prefer this solution. And if in the alternative solution, you are going to see a very, very big coefficient. Now you can see we have a unified way to look at the cyclic graphs and acyclic graphs. And in ICA, when you do ICA, you can have very small coefficients. In the previous solution, we have to cut off, we have to set those into 0 in order to proceed. Now I don't care. I just want to find a permutation or call the order or call the model where the self-influence is as small as possible. If there are no cycle, then the self-influence will be 0, right? And if I happen to have a very small value here because of random error, then for the right model, you can see self-influence is very small because A times B. B is very small, it's very small. But in the alternative one, the self-influence will be 1 over A times B, which is huge. I will still prefer this solution. Okay, and this part is not this part. Sometimes it might be kind of mathematical, but try to see the intuition. And we are very optimistic. In practice, even if there are cycles, you can recover the color model because you would like to have the kind of reasonable color model, which is kind of stable.
So basically, we're kind of constraint, having some constraint on that mixing matrix to hunt for the stable system.
Yes, yes. So you prefer kind of a stable one, or you prefer the solution in which the final inference, right? Self-inference is as small as possible. Yeah, good. Now you have a unified way. I mean, no matter you have cycles or not, you can always find the best solution. That in the solution, you can also handle the acyclic model. Okay. Now remember previously we even had a cycle in the previous solution on the Galton's family height dataset. We have a self-influence loop for father and mother height. Remember? It's because we just try to estimate the relations. And actually you can verify or you can falsify the cyclic causal relations because the noise terms were still not really independent. But if we really have a cycle here, the noise terms are still independent, right? Let's see that's more related to selection bias. In theory, you can distinguish between acyclic model, cyclic models, confounded case, and selection bias. So if you have data, in many cases, you can really see which one is really the case. Okay, good. Right here, we still have, suppose you have m variables, you still have m independent components, and the problem is W cannot be permitted to be lower triangular because it's not acyclic, but you don't really care very much. As you can see from here, this is something missing here. This is 1.2. So you have the simulated data, original one, and then you can go from this one to the alternative one. I minus B is W, I can have an alternative solution, as you can see from here. This is the original solution, and this is the alternative solution. Okay. You can see the graph here. This is the original one, and this is the new alternative solution. This is minus 0.3, this is the minus 3.3. Minus 1, minus 1. 2, 0.5. Oh, give me 1 second. time to do a reflection. Okay. So you can see the correspondence. And there's one more difference right here. Just one more thing. Regarding the skeleton, now you can see the skeleton is slightly different. Here we have influence from 1 to 2. Here we have influence from 1 to 4. That's another difference. Why? Because previously, we have an equation involving x1, x2, and x4, where you put x2 on the left-hand side. Now, because the color ordering thing, you have the same equation, but you have to put x4 in that equation on the left-hand side. That's a way to explain the generating process of x4. That's the only difference. Okay. So in the linear and Gaussian case, and also in a lot of nonlinear cases, we can really recover cyclic models, especially if you would like to assume that the system is stable in some way. And you can see the difference. And here I'm talking about a very simple case where you have only a single cycle. The same thing holds true if you have multiple cycles. And even if the cycles are kind of partly overlap, you still have similar solutions, similar conclusions. Okay, so cycles are not a problem. And in addition, we have a very natural way to interpret the cycles. They are nothing but a compact way to look at the original causal influences in the causal process, right? Originally, they have some time delay. Now there are no some time delay. That's why they appear to be cyclic. That's it. Okay. Questions? Here you can see a simulation study, 2-1, and you can estimate, you can apply the method. You can see there are only 2 solutions, as you can see from here.
Or one of them is more stable.
Oh, good. So they are, first of all, they are equivalent in terms of the observed data. They are observationally equivalent, meaning that they can really give rise to the same distribution for the measured variables. However, in terms of stability, they are very different. Why? Because for one of them, in this single case, for one of them, you can see the influence, self-influence from x1 back to itself, right? Is 1 over b. But for the other model, it's 1 over a times 1 over b. So if ab is small, a times b is very small in a stable system, then 1 over a times b will be huge. It's not stable. So they are different. If one is stable, the other is not stable.
So one is unstable. I will just discard the unstable.
Generally speaking, yes. Yes. Yeah.
For the unstable one, you're not able to generate the data from those systems. The system will explode. So they are actually not observational equivalent because you cannot find the data set that's generated by either of couples of them.
It's a very good point. So the question is, basically, if the system is not stable, I cannot generate data because after some time, right, it will explode. Yes. Give me 1 second. How can I give this? That's a very good one. So first of all, they happen to clearly they have the same distribution. But even if they are very large, because of the kind of coupling relationship, you can still generate exactly the same data. As you can from here, it's exactly the same. Let me see whether 1 over, if the coefficient is larger than 1, then system must be. But if you really want to generate data in according to this alternative solution, right? What can you do? Let me see. Anyone would like to give a response? So if the alternative solution is not stable, how can we say they are observationally equivalent? Because you believe that in the system that is not stable, you cannot generate the same data because the data will generally explode. Any response?
I think the error term should also do something, right?
Error term is
So
right here.
balance out that
The error term would be different, very different. However, the scale or the variance of the error term is fixed. Then after some steps, right, we still explode.
cancellation.
Sorry,
It's like there's a matrix there. One over one minus.
can you see louder?
So there's some cancellation.
Yeah, what I'm trying to figure out what kind of cancellation we have right here.
Yeah, like the error. So it is like there's a little thing is
Yeah, what's exactly the cancellation here? How? Yes, right here.
look at this text, you look at the first end.
Mm-hmm.
And you got the first one of both the X, the first one,
Yeah, good. Yes, you're totally right. You're totally right. That's exactly the cancellation. So this is for the following reason. Let me put it in a different way. Here, the coefficients are very, very large. You generate x1 from x2. And you know that x2 and error term are heavily dependent. So the large variance canceled out. That's why you can still have something stable, because you have a cancellation. Remember, x2 here and E1 here are dependent, right? So they are heavily dependent. As a consequence, those things just got canceled out. You still have a fixed distribution right here. However, you can also see that there must be some kind of precise cancellation in order for you to have a system. That's what I mean by kind of instability, right? So yes, that's it. Very good question. Wonderful. Any other questions?
data or the aggregated data.
Yeah.
So
Yes.
So
Wonderful. Yeah. Wonderful. So the question is, yes, here you can do aggregation, but you may have Gaussian distribution for the aggregated data because it's a sum of a lot of factors, right? First of all, in practice, you may not want to use a very large value for error. And second of all, central limit theorem is really important, but we also have technical condition there. So very oftentimes, for instance, if you consider stock market, actually the daily return is not that Gaussian, right? So in many cases, you can avoid that thing. Of course, if the distribution is really if the original variables are really IID, then you are totally right. As time goes on or as K increases, the distribution of the aggregated variables will be getting closer and closer to Gaussian. In that case, you should use the right value for K. For instance, if you have one-time delay, in practice, you can find that if K is something like 4 or 5, then you can recover this causal model in a very good way. Very good point. Excellent. Any other comments or questions? Okay, now let's go further. In this part, you saw how we dealt with the linear non-Gaussian case. I should give a comparison between the conditional independent based method or constraint based method and the new method, functional causal model based method. First of all, with the conditional independent based method, you don't really care about functional class. You just want to use conditional independent relations, right? So in this sense, it's very general. However, we also know that in practice, if you want to test for conditional independence, usually you have to assume something about the process, right? And furthermore, one big thing that right now, today, we can avoid the faithfulness assumption, and we can go beyond the equivalence class, and we can even deal with latent compounders in a good way, right? Not to mention cycles. We can also deal with cycles in a very good way, because we make additional assumptions. In the linear case, we assume non-Gaussianity, but generally speaking, it holds true if the model is nonlinear. Is linear, and if the relations are nonlinear, then even if the distribution is Gaussian, the same thing holds true. By the way, Gaussian distribution is so weird because of linearity assumption. Gaussian distribution and the linearity of the relationship are coupled. In the linear case, Gaussian distribution weird. In nonlinear case, another distribution might be very weird, which is not Gaussian. Okay. Now let's go further. How can we deal with all those things, including nonlinear functions, memory error, selection bias, missing data, and so on? There are so many practical issues. Basically, here is rather kind of exhaustive, right? You can deal with all of them. Remember, in causal discovery, we are not trying to find a kind of descriptive property of the data. You want to recover the truth. And in the data, you can even consider all those things as part of the generating process. Selection bias is a part of the generating process, right? It's how you generate the data. Memory error basically is in the data you observed. That's why you can think of causal discovery as a way to really look into the observed data to recover not only the causal process among the variables of interest, but also how you sample the data or how you generate the data from the underlying true process of interest, right? It's a basically holistic thing. You have to measure the data to really see how X and Y are related and how they are generated, how the data are generated from them, right? So that's why we cannot simply ignore those practical issues. However, if you want to make prediction, don't care. You just make use of dependence. Now you want to find the source of the dependence pattern. So before taking the break, let's again look at the practical issues. Now have a closer one. So here, in some cases, you may discretize the continuous variables to generate, say, binary or 5-valued, right, observations. Then you have error, and you may have independent random error, and you may have kind of uncertainty in the measured data points. All those things can be considered as measurement errors, right? You have error in the measured values. You can deal with all of them. You have selection bias. Here, I use this particular kind of node to denote the selection. You can see in this case, S variable is determined by W and X1 in a probabilistic way. If S is 1, the data point is in the data set. If S is 0, it's not there. You don't have the data in the data set. So this is how you can select the data points to produce a data set. And then in the data set, you only observe the data points with S equal to 1, right? This is the selection process. And later you can see how you can deal with some kind of selection bias. And right here, the listening compounders, as I just mentioned, very often in traditional causal discovery, you care about the relations among the measured variables, but not the latent variables. However, in many cases, you may want to go to the world of the latent variables or concepts, right? And then you want to see what's going on. We have this ability. If we look at the raw image pixels, we can automatically infer the underlying concepts, right? Like a color, shape, and so on. How can you allow machines to do the same thing, right? That's the problem we want to solve. And specifically, we call this problem called representation learning, because you have to find the right representation. You have missing value right here. You can see this is a kind of real data set. You have missing, some entries are missing. Missing value is a causal problem because why the value is not here is a causal question, right? There must be a reason. For instance, this one is missing because I don't measure another guy, or because this value is too high, and so on. Then you can also incorporate that as part of the causal graph and the causal model. Everything is transparent. You can even discover the whole causal graph, including why values are missing from by using some kind of causal discovery method. I will briefly mention it. And causality time series, you saw it. I'll skip this part. And we can also do analyze the non-session data, as I just mentioned in the morning. Now let's take a break. Okay. Here, more complete. I just had another discussion. So here, in the first case, we assume the system is stable. That's why we have the second equation. If the system is not stable, you even don't have that equation, right? By that equation, I mean xt equals b times xt plus noise, right? So even if you can find the equivalent model, it does not mean that there exists the process right here corresponding to that model, because that model, if it exists and if it's not stable, you cannot have this equation since you don't have the equilibrium state situation. You cannot make them equal. You cannot make them equal to each other. Okay, so that means indeed in this very simple situation, the solution is kind of unique if you can find the underlying causal process instead of a description of the process with the structure equation models. Okay. Now what's left? So first of all, let's have a look at the nonlinear models. You see identifiability and how we can estimate it from data very quickly. Again, you look at those things, you can see the relations are kind of nonlinear, right? Very often times the relations are nonlinear. And clearly you cannot say we can use a nonlinear function with additive noise. Noise changes, right? Change a lot. Noise change a lot. Noise variance or noise level change a lot, right? So we have to find a way to capture such a causal influence, right? First of all, you saw this part before. We already have a constraint. Now we are going to see that if you are willing to make kind of almost any kind of constraint on the function f, all of a sudden you have identifiability. Thank you for saving me. So here, let's start with the nonlinear function plus additive noise right here. I just try to make sure everything is kind of intuitive here. Y is a nonlinear function which is like piecewise linear for illustration, for illustrative purposes, plus independent noise. If you look at x given y, now you can immediately see that, oh, there's something very weird. So the noise level will be very sensitive to the location y, right? That means no matter how you do regression from y to x, the error will definitely be dependent on y. Again, you see asymmetry. In the linear non-Gaussian case, you saw it. Now in the nonlinear case, even if the noise is Gaussian, you can still see the phenomenon. They are not symmetric. In the reverse direction, the error will be dependent on the predictor, because clearly the noise, the shape of the noise distribution, or specifically in this case, the support or the range or the level of variance of the noise will be dependent on y. As a consequence, they cannot be independent. Okay, so you saw it. And then let's look at this model, post-nonlinear model. It was first given a long time ago, and then we gave some more theoretical studies later. Without the strong prior information, you would like the model to be rather general. At the same time, you have to show that the causal direction is identifiable according to this model. Otherwise, you cannot distinguish between cause and effect. So at that moment, we thought, yeah, three factors are very essential. First of all, you may have nonlinear effect of the causes, and then you have noise effect, inner noise effect, and then you have sensor measurement distortion. Very often times we have to use the instrument, right, to measure things. And when we measure things, we may introduce two kinds of annoying things. One is a distortion. You use this instrument to measure the gene expression level. In order to see the gene expression level, you might need to apply something in order to really see the information, right? And that thing can really introduce some nonlinear transformation. And later you can see that process can also introduce additional noise, known as measurement error. Good, for now, let's consider nonlinear transformations. Then you have this model right here. Clearly, linear models, nonlinear additive noise models, if you drop this guy, are special cases. And even if the noise is multiplicative, as you can see from here, it's also a special case. You have F2 here, F1 here. They are still independent, right? Here you can see the scatter plot of the finished square feet and the sales price of a lot of houses in Boston. Do you think the model is linear? Do you think the relationships right here is linear? Yes? No? Why did you say it's not linear? You mean because it's kind of you might because okay. So what if that part is a kind of you have a linear trend line? What if that's the case? Would you say it's linear? Okay, we can save time. I know many of you don't think it's linear. Why? Because when we say linear, we mean the following thing. You have a linear model with independent noise. That's very important. Here, clear noise level will change a lot if you use a linear model or even nonlinear model with additive noise, right? So that part is crucial. We assume the noise is independent from the input. However, in this case, if you use this kind of model, then the noise will be independent from that because this function right here can do adjustment. After that transformation, if you take the logarithm transformation, and then you can see, yes, the noise will be somehow independent from the input. This is clearly nonlinear, very nonlinear actually, right? Approximately speaking, this one follows the post-nonlinear model. Okay, it's very mathematical. So now you have a nonlinear model. You have functional class as you can see from here. Remember, in the linear case, we can use the independent noise condition to find direction. You can do regression in one direction, test for independence, and then you can consider the other direction, then you have a conclusion. In the nonlinear case, generally speaking, if you have two variables, you can do the same thing. I can fit the model in one direction and find the residual right here. And then I can do the same thing in the reverse direction, and then I try to see whether the residual is independent from the input. As you can see from here, the problem is how you can estimate the two nonlinear functions. So here, it's not difficult. This is some kind of constrained nonlinear ICA problem. You want to transform x1, x2 in a specific way in order to recover E2, which is supposed to be independent from x1. And then this is almost the same as regression. When you do regression, linear regression, you want to minimize the error, right? Equivalently, you can say you want to make the error independent from the predictor. They're the same thing, right? If you consider the condition likelihood, then you can see it's basically the same thing. So here is the same thing. You want to minimize the mutual information. However, in many situations, you cannot achieve that. For instance, if you go to this data set, you do nonlinear regression, and then the error, you try to make the error as independent as possible from the input or predictor, but you cannot achieve it, right? In the linear case, if it's non-Gaussian and if the direction is wrong, you can make them uncorrelated, but you cannot make them independent. Although when you do regression, you actually want to make them independent, but you cannot achieve it because of the limited capacity of the model. The same thing happens, as you can see from this result. This is the first data set, remember? X1, X2, you are given the data. If you assume X1 causes X2, you fit a model, you estimate the residual, they are kind of independent. In the reverse direction, this is the scatter plot of the estimate noise and X2. Clearly, they're not independent. Okay, so we prefer direction from X1 to X2. Actually, X1 is the altitude, and X2 is the temperature for more than 300 cities. Okay, temperature should be caused by altitude, not the other one. So similarly, you can see this kind of phenomenon across many data sets. Good. empirically speaking, even with this very flexible functional model with two nonlinear functions, you can distinguish between cause and effect. By theory, do you really trust it? How can you really give a rigorous guarantee that we can trust the result if you have enough data? This is identifiability guarantee. We have a standard way to establish identifiability of causal direction. So given the distribution for x1, x2, or given the data, you just try to see if the direction goes from x1 to x2. If this is the true direction, you want to see whether in the reverse direction, you can still find the independent noise, right? So in order to do so, you assume that the reverse direction can also produce independent noise with the post-nonlinear model. And then you can see whether it's possible for you to have this phenomenon. And then you can solve the equation right here. Fortunately, this equation is kind of has a bilinear form. Then you can solve this differential equation. Finally, you can see there are only 5 situations in which you can also find the independent noise in the reverse direction. The first one right here is the linear Gaussian case. You know it. And if both functions in the causal direction and the reverse direction are linear, then this is the only situation. Then, you know, or if it's not linear Gaussian case, then in the linear case, the causal direction is identifiable. However, in the second one, I can see it's interesting. In one direction, it's linear, and the distribution is very specific. It's like a Gaussian distribution. It has to satisfy some particular form. Okay, but in this case, you can actually find a nonlinear function in the reverse direction with independent noise in the post-nonlinear model. However, in each of those cases, the functions and the distributions are very specific because they have to follow specific forms. Then we can say, generally speaking, the chance for you to have those cases is almost 0, right? Because they have to satisfy particular forms. In practice, it's not likely for them to follow a specific form. So, okay, this is interesting because you can really just see all those cases in which the causal direction is not identifiable for data generated by this very flexible model, post-nonlinear model right here. For data generated by this one, only in those 5 situations can you see the symmetry between cause and effect. They are very specific. And interestingly, you can see if both directions are linear, as you saw from my previous illustrations, right? Use the linear models in both cases, in both directions, then you cannot find the independent error term in the wrong direction. Even if in this case, but you can see the asymmetry. You can see the symmetry because all those 5 situations are unidentifiable situations. You can see the symmetry. However, in the other direction, the function is not linear. Okay, good. To conclude, generally speaking, even for data generated by this very flexible model, the direction is identifiable. You can see the asymmetry. Since this model contains linear model and other things, nonlinear additive knowledge models as special cases, the same thing holds true. Then we can trust the result. If you have enough data, we know, yeah, if I find this direction, I can trust it because I know that in other direction, it cannot be the case. Okay. Yeah.
According to this formula in here, so what's the difference about this formula and the box transformation in the traditional, linear regression case? This seems more traditional.
Wonderful. So the question is, what's the difference between, for instance, this model, right, and the traditional model like Cox? Transformation model to correct the additional nonlinear transformations, right? Very good one. I would say, first of all, that illustrates that very oftentimes we have additional transformations. You have to apply a suitable transformation in order to make the relations very nice or simple or beautiful. right? In some cases, you have independent noise. In some cases, you may even have linear relations. So, however, in statistics, usually you try to see the properties and try to have parametric models, right? And here, they are just special. That's a special case of the post-nonlinear model. The difference is that here you can automatically learn both functions just from data. If you use this is a specific procedure, we also have other procedures. So you can just estimate those functions. If they happen to have that form, you can estimate it. Even if it's not the case, you can still do it. Okay? So it's more general. And at the same time, the example you gave illustrates that in many cases, we need to consider additional transformation in order to really discover, right, underlying relations. Good? Yeah.
Yeah, so is there any way to generalize this to multivariate case?
Yes. They are not, go ahead.
I guess in terms of both theoretically and empirically.
Yes. First of all, in theory, remember I said that causality is basically a two-variable problem. If you fix other things, condition other things, then it's always a two-variable case. So now in a two-variable case, you have identifiability. That means no matter how many variables you have identifiability. It's kind of trivial. You can easily do so. Okay, because the conditional distribution, right? And second, regarding the method, there are multiple ways. Actually, recently, I think in the last 2 years, 2 new methods were proposed. In our original method, we just use kind of this method and extended Gaussian process regression thing to estimate noise and see whether they are independent. If you have many variables, what can we do? There are 2 ways, at least 2 ways to solve the problem. One is to first apply conditional independent Bayes method. Then you have the equivalent class. And then you can also have the direction for some of the edges. Then you can use this model to determine the direction, right? So you can do so. And alternatively, you can also directly estimate the relations among multiple variables by doing a specific type of nonlinear ICA, as you see. So from here, if you have many variables, still you can do similar things. Although in practice, it might be kind of complex since you have so many nonlinear functions to estimate at the same time. Okay, so still, as I just mentioned, in the last 2 years, 2 new papers were published. I think new methods will be published in the coming years in order to make this really kind of useful or practical. And I was surprised when I saw the 2 new papers because this one was published 14 years ago. And just recently, yes, basically people started publishing better methods in order to estimate such model from data. Did that answer to your question? Okay. Any other questions? Okay. Okay, so I don't think everyone can hear yet. When you say,
You mentioned the 2 papers, you think they do a better job estimating F1 and F2?
yeah, you are totally right. Yes. So they try to make some assumptions. For instance, one paper basically relies on order correlation. So you can see why, because this F2 does not change order correlation, right? And so on. Yes, they are trying to either have a better way to estimate F1 and F2, or try to find the causal structure even without explicitly estimating F1, for instance, or F2, the outer function of F2. Is that answer to your question? I can send you the 2 papers. Yeah. Okay. Now let's go. Nonlinear model is good. However, in the linear case, remember some of you asked a question. I think it's Yachi, yeah. You asked a question regarding transitivity. Do you think nonlinear functions, especially nonlinear function with additive noise model, right? A model of nonlinear function with additive noise is transitive. X1 causes X2 with nonlinear influence and additive noise. X2 influences X3 with a nonlinear function and additive noise. Good. Intuitively, you may say, in this case, even if I ignore X2, I can say X1 influences X3, right? Because causal influence itself is usually transitive. But if you look at scatter plot of x1 and 3, you can see something very weird. Clearly, there are no additive noise. The function could be very weird. This means that the functional class is not necessarily transitive. Of course, in the linear case, everything is transitive, right? The form is transitive, but in the nonlinear case, it's not. Is that a good thing or bad thing? In practice, right, we have causal inference from this. I don't want to give real examples. So we believe x1 influence x2, x3, although there's something in between, right? We believe so, but the distribution can be very weird, and you cannot use additive noise model to explain it. Do you think this is a good thing or bad thing? First of all, it's bad, because now if I fit, say, even personal linear model to the data, I cannot really say the error, the ultimate error is independent from x1, right? And second of all, it might be a very good thing. Why? Because if you believe each atomic interesting causal influence follows the nonlinear function with additive noise, if you believe so, then with this phenomenon, you know, I have to introduce, or I have to discover that guy in between in order to explain the relation, right? That means we have the potential to really discover hidden variables in the system. That's a very good thing, because scientific discovery basically is about how you can discover the right quantities, right things from observation of data. Here, even if that guy is not, say, common cause of anything, it's just an intermediate variable, but still, in some cases, you can recover the intermediate variable from the measured variables, right? Okay, so you look at this picture before. Now let's look at the memory error. First of all, let's look at memory error is almost everywhere, right? In gene expression data, you have memory error in almost everywhere. So this is the original causal process. G tilde is the true one, as you can see from here. This is G tilde, it's hidden word. Before we measure it, it's there. We try to measure it, but when you try to measure them, we add some error. Specifically, for now, let's look at the independent memory error. So each of them, the measured variable is generated from the underlying true variable together with some measurement, some error, right? So this is the whole causal graph. If you want to see how the measured variables were generated, then this is the whole graph. Good. Now let's try to see the effect of measurement error. First of all, suppose we want to use the conditional independent Bayes method. Let's look at one example. In the original world, causal world, 1 and 3 are independent given 2, right? 1 and 3 are independent given 2 because they are separated by x2, right? At tilde. Good. Now, if you just work with the measured variables x1 to 3, do you think x1 and x3 are conditionally independent given x2? Yes or no? Yes? Oh, we know that in the original world, x1 tilde and x3 tilde are independent given x2 tilde. Now we are talking about measured variables, x1 to 3. Do you think x1 and x3 are independent given x2? No. No, right? Depends on
the error.
Depend on what do you mean by that?
I mean, how much error is, how much is the measurement error?
Yeah.
How much is the measurement error?
Yeah. Okay. Good. So in principle, you say, generally speaking, they shouldn't be conditionally independent, right? Because they are not deseparated. Remember, when you try to see whether deseparated, you have a complete graph. You want to have all those relevant variables, and then x1, x3 clearly are deseparated by, say, x2 tilde. But x2 tilde is not measured. We cannot condition on such a guy. If you don't condition on anything, they are independent because they have some common source. If you condition on x2, they are again not deseparated. So generally speaking, x1, x3 will be conditionally dependent, meaning that if you apply, say, PC to the data, you are going to have a link between x1 and x3. In this case, you are going to have a complete graph. 1, 2 dependent and conditional dependent. 1, 3, the same thing. 2, 3, the same phenomenon. That's why you have a complete graph. That's very poor because you cannot recover the truth. Why? Because you don't have access to the original variable. And when we try to see the relation, we want to recover the relations in the true world, right? Regarding genes and so on. We don't really want to say, oh, I have to say something, I have to find a relationship, dependent relationship among the measured variables. No, you want to say something about the underlying true variables. Okay, and right here you can see this phenomenon. As you increase the level of measurement error, as you can see from here, this is the level of measurement error, relative level. The correlation between 1 and 2 will becoming smaller and smaller. Why? Because when you include the measurement error, independent errors are independent, then the more the independent error you have, then the more independent they are going to be, right? So this part, the correlation will be decrease. At the same time, you can see the conditional partial correlation between 1 and 3 given 2 will increase this way. Okay, so now it means that with measurement error, the world is kind of blurry. Independent variable, conditionally independent variables may become conditionally dependent. Originally dependent variables may become less dependent. Okay, how can we solve the problem? Now we can see with the condition independent based method, we have to do some correction, right? You can see some kind of heuristic way to do so. I will come back to this one in a minute. Right here, as I just mentioned, because of measurement error, originally conditionally independent variables will become somehow conditionally dependent, right? And dependent variables will become less dependent. So right here, that means for the test, the p-values, the distribution of the p-values will be kind of wider because dependent variables will become less dependent, right? So that means for the dependent cases, the distribution of p-values will be wider, right? And for the independent things, it's the same because if they're independent, then the p-value is uniform, follow the uniform distribution. So if it's wider, what can we do? We have to distinguish between the dependent situations and independent situations. What can we do? In this case, we can just try to use a smaller significance level as a cutoff kind of threshold in order to distinguish between the two cases. I mean, this will be completely heuristic, right? This is the complete heuristic. However, you can see it's phenomenon. It's useful. For instance, if you have data with noise, memory error, very oftentimes you can see with a very small value for alpha, the result by PC is sensible. Okay, that's one way to correct it. Let's go back. There are principal ways, but they are more complex. You may want to say that, yes, I don't want to use memory condition independence. I can use independent noise. I can use linear non-Gaussian models, right? So the same phenomenon will happen. Right now, you can see this is the scatter plot of x1 and x2. And here for simplicity, I just use uniform distribution for all those kind of noise terms. Yesterday, I talked about this pattern, right? So now you can see this is the scatter plot of x1, x2. If you have the scatter plot of x1 tilde and x2 tilde, it's perfect linear model with independent noise. Now, do you still have independent noise? If you have look at the scatter plot of the error and x2 regression error and x2, you can see, are they independent? No, clearly right now, because the distribution of this guy is sensitive to the value of x2. So now, because the measurement error is like error in measurement model in statistics, right? So the regression residual will not be independent from the measured variable corresponding to the cause, measured variable corresponding to the cause. So meaning that if you apply linear non-Gaussian model, you can you may also see the same phenomenon. You can have extra edges because the error is not independent from the cause. Okay. Yeah.
But in principle, if it's large, it wouldn't be independent, but if you compare the two, they both would not be independent, but one should be more dramatic.
Completely agreed. Yes. In practice, if the memory error is not very very large, then very often times you can just do the comparison. So especially if you have some idea about how large the memory error should be, then you have some kind of confidence. Yeah, to the right. Yeah. Wonderful. So here you can see this alternative representation of the memory error model. Basically, instead of using the original model, I can simplify it. In this case, maybe I should go. Let me see. Where? No, I think there's another graph. Yeah, in this graph, x1 called x2 and x3 also called x2 in the true world. Now you just measure their noisy versions, right? x1 to x3, they are noisy versions. And then you can see in this case, actually, there are only two latent common causes, two latent compounders, x1 tilde and x3 tilde. As you, right, x1 tilde, x3 tilde. And their noise terms are independent. So this is the noise in x1 tilde, this is noise in x3 tilde. They are common. All the remaining things will be specific. They are still noise. I mean, this is another way to put the model. But if you put the model this way, you can see this is either a effect analysis model, mix of observed variables, loading matrix, common factors, noise terms, right? Or overcomplete ICM model with a lot of noise terms, right? So you can, under some assumptions, you can estimate those models. And then under some further assumptions, you can go from this model back to the causal model right here. That's the idea. So we did a study a couple of years ago, right here, yes. So in the linear Gaussian case and the linear non-Gaussian case, you can see what you can recover. Basically, the message that follows. For instance, in the linear non-Gaussian case, then although you cannot recover the true causal graph, you can recover the causal order in some way. So that's informative enough, very often times, right? Okay, I'll skip that. And yes, last year, our student Haoyue also published a paper in which we can use another condition called the generalized independent noise condition, which I will talk about tomorrow. To simplify the procedure, you just do independent test for combination of the measured variables, and then you can say something about the underlying true causal model in this case. If you want to see details, look at the, oh, I forgot to show this part. If you want to see more detail, talk to me, or you can ask me for the papers. Okay, I'll skip this part. You can see what can be recovered. It's called ordered group decomposition. So we can divide the variables into different groups and then still recover the causal relations among causal directions among the groups. Now you can see some simulation results. This is a true graph, and this is estimated by linear non-Gaussian method. And right here is the estimated when you take into account the influence of the memory error, right? You correct for it. So you can see this one is almost identical to the true one, but with the linear non-Gaussian method, you can have extra edges, and some relations are wrong. Okay. Okay. Now let's.
So try to eliminate the measurement error using some other steps to measure and then do the causal discovery. Is that a good or bad idea?
Can you give an example regarding how you can eliminate the memory error?
I am not sure, but I was just wondering if there existed some.
Something I think you were talking about the missing data. You can use causal methods to find missing data, right?
Yeah, missing data, yes.
Yeah, some causal method which related to some other, process variables that can impact the noise or produce the noise.
I would say for missing values, right? You can try to impute the missing values by making use of causal mechanism. For memory error, the problem is as follows. usually when you try to impute the missing values, you don't really, you know you cannot recover the truth, right? You just recover kind of the value in a very rough way. Then it's good enough. Because you are not going to, generally speaking, you are not going to use the imputed values for causal discovery. Maybe you want to do estimation. But in this case, you want to find a way to correct for the memory error in order to find the correct causal structure. That's why how you can do so is really crucial, right? And generally speaking, if you know something about the error, for instance, if you know error is Gaussian, then you can find a better methods. For instance, you can find a method that is invariant to the Gaussian influence. With a high order set, you can do so. And generally speaking, without the strong assumptions, you cannot do so because it's so hard for you. Let me go back to this picture. You see why. For instance, for this guy, for X5 or X4, in the original causal process, it had noise. Now you have additional noise. How can you distinguish between the two types of noise, or the error and noise, right? That's a critical issue. Without the very strong assumptions, you cannot really recover them. Is that answer to your question? But it is possible if you have strong assumptions. We are also on the same page. Cool. Selection bias is in your data, basically, in almost all situations, you have selection bias, right? If you have data collected in hospital, yes, because according to the definition, the chance, if the chance of including a particular data point in the sample or data set you have depends on some attributes of the data point, then we have selection bias. Clearly, if you collect data right here, they don't feel well, right? This is a feature the data point depend on. Clearly, you have selection bias, right? Of course, you may have different kind of selection bias. For instance, with selection bias, a lot of things will become very messy. Suppose it's a true causal model, X causes Y, with a linear model and uniform noise. It's very beautiful, right? Now, suppose you have selection bias, very simple one. So if Y value is very high, then the chance for you to have the data point is relatively low. Remember that one. Mother's height and father's height. Remember, right? Given this one, if the value, given the mother's height, body height, if father's body height is very high, then the chance for you to have that is very low. For instance, right? So right here, you can see this is the scatter plot after you apply this selection procedure. It looks kind of similar to the previous one, right? They're very similar, but you can see here you still have a lot of data points. Here you have fewer. And then a lot of things will become weird. For instance, the regression line will be different. It goes from this one to that one. Regression line will be different. And after that, the regression residual will not be independent from the predictor. Later, I will show why. Okay, so selection bias is really horrible. It distorts a lot of things. Now let's see the effect of selection bias in a very quick way. Suppose this is a true causal process. And we have S right here. If you have S given this way, it's a selection variable. If S is 1, we keep it that point. Otherwise, we don't use it, right? In the sample or data set, you don't have that point. So here, suppose this is the truth. What do you think the discovered causal structure will be if we have selection bias right here, depending on X1? If we select data points according to the values of X1 in this case, and you apply causal discovery method to the data, select the data, can you recover this graph? So now comes the essential point. Maybe I should just give the next slide, and then you can see why we can do so. Oh, I gave it here. So for the selected data points, you have a new distribution, which is the conditional distribution of the data given S equal to 1, right? So you always condition S. Now, if you have S1 here, S here, I can just draw it. When you try to see deseparation relations right now, you always condition on this guy. because you always work with this condition distribution. And in this graph, if you further condition on this guy, you don't change any deseparation relations, right? So if you have selection only on X1, totally fine. What if you have selection on X1 and X4? Now you are going to see that X1 and X4 will not be deseparated, even if you are given X2 and X3, because of this open path, since you are condition on S variable, right? So if you apply PC here, you are going to see this extra link. Right? Select bias is almost everywhere. So we analyze the gene expression data in single cell gene expression data, and you can just see a lot of dependent relations. And for some of the dependent relations, we don't have a causal explanation, but still you see dependence, because particular genes have to function in some coupled way in order for us to survive, right? So you can see dependence caused by selection in biology almost everywhere. We don't have a causal explanation, or we don't have a causal inference between them, but they are dependent. Okay, so now let's go. Here you can see a categorization of the selection bias problem. You may have selection depending on the causes, or causes but with a confounder with Y. Here, this case was discussed by Heckman, from Microsoft Research. So this is called outcome dependent selection. And if you have data in collected in the hospital, very often times you have this case. Why is the disease? So whether this person is in hospital depends on whether the person is ill, right? In a probabilistic way. And right, this is far more complex. Here we cannot say very many things. Okay, let's look at this phenomenon right here. This is called outcome selection bias. And in this case, clearly, it's interesting that you can recover a lot of information from the bias data. First of all, the causal direction is still recoverable. And second of all, under further assumptions, you can even recover the quantitative causal model, causal inference. Okay, if you are interested, you can look at the paper. And right here, you can see how the distribution of the observed data is related to the original data, original distribution without selection. This is the distribution of XY right here after selection. So you have to condition on S equal to 1. And then if S depends on only Y, then after some kind of transformation, you have this equation. Now you can see the new distribution is nothing but the original distribution times a function of Y, because you have selection depending on only Y. It's very simple. If you realize that, you see, oh, I can really figure out the selection, whether they are the selection bias in the data under some assumptions. And right here, I just showed this one before, right? And I said, if you have selection Y, the regression can be very different. And here you can see the scatter plot of the arithmetic noise and X. Are they uncorrelated? This is a linear regression residual. Do you think this guy and this guy are uncorrelated? By construction, it's regression. It's a regression residual and a predictor. They are uncorrelated. Although it's very weird, right? Why become selection? So here you can see you have more data points here. That's why the correlation is still 0. But because of selection, the process you can see the residual will not be independent from the hypothetical cause anymore. You can detect selection and you can go further under some assumptions. Okay, I will skip this part because it's kind of technical. This is one application. So here we analyze the data. Here X is age and Y is blood pressure. We have the data basically collected in the hospital. So you can see the data points. And then this is the beta function regarding how likely it is for you to have the data point in your data set. Okay, the higher this value, the more likely it is for you to have the data in your data set. Now you can see this is the estimated function. It's very interesting because right here it's kind of flat, but it's very high if the blood pressure is very high. It's kind of reasonable, right? Because if the blood pressure is very high, it's very likely or more likely for this person to be measured and included in the data, in the data set. You can really recover all those things from data under some assumptions.
So you can weight your data and then use the kind of usual causal experiment.
Wonderful. Yes, if you have beta, then you know how to do the weighting thing, right? Essentially, you want to, if you can make beta disappear in this part, if you can make beta disappear, then you have the original distribution. You can do anything. That's totally right. The problem is how you can estimate beta. Under some assumptions, you can. Okay, this is the selection. The last part. Sorry, it's very fast, I know, but without finishing this part, tomorrow we are not going to finish kind of some other parts which might be more interesting. That's why. Now we have data with missing entries. First of all, let's distinguish between missing values and selection bias. Right, this is a problem we just discussed. Here you can see I have missing entries, but I still have value for some other variables, right? For those records, you can see that. However, in selection bias is different. If some condition is not satisfied, then the whole record will disappear. It's not in the data set I analyze, right? So they are closely related. At the same time, the definition, their definitions are different. Here, by missing values, I mean, you still have the record, but you don't have the value for that particular variable. First of all, according to Donald Rubin, you can just formulate why the values are missing with the so-called missingness graph. Here you can see the three different things. And I will talk about those three situations in a minute. Basically, if you have such data, and if you try to find the underlying causal structure, what can we do? Some of you clearly, right, were faced with data with missing entries at some point. What did you do?
Estimate.
Oh, imputation, right? You want to impute the missing values. That's kind of almost a standard way, but that's very dangerous. Because clearly you cannot estimate the values in a very good way, and then you introduce error. If you introduce error, we know even conditions in interrelations can be very different from the original ones, right? Is there any other way?
If it's missing completely at random, you can exclude the observation.
Okay, how can you know whether it's missing at random or completely at random,
That's
right?
another problem.
Okay, that's enough. So you assume that, then you can go. Good. Is there any other way? One method is called test-wise deletion method. I don't throw away the whole record. If I try to see whether X1 and X2 independent given X3, right? I just make use of all the records without missing values for X1, 2, or 3, and 3. That's it. This way I can still use a lot of record. Although I have missing value here, I don't care. As long as I have the record for X1 to 3, right? That's why it's called test-wise deletion. For this test, as long as I have values for X, Y, Z, I keep the record. This way you can have a lot of new data points. You don't have to throw away all the records with any missing entry, right? Good. Let you see whether those methods are sensible. And specifically, you can see whether you really have missing completed at random. You can verify that. So here, this is the missingness graph. R is basically a set of missingness indicators. If R is 1, then the value of this variable is missing. You cannot see it. If 0, you have it. Right? It's missing the graph. It's the indicator. Very simple. Then have those graphs. Then we can just have those 3 types of missingness. This is missing completed at random. here you have missing indicator. Missing is indicator for Y. And this guy, you can see, as you can see from here, the cause of missingness is purely random. So this guy is not adjacent to any of those variables because it's independent from all those variables. It's completely at random. Good, as you just mentioned, if that's the case, it's simple. I can just ignore those missing entries, right? In this case, it's a missing at random. So here, you have missingness and Y is missing right here, depends on the value of W. However, W does not have missing values. Okay, this is missing at random. The name is kind of controversial, right? When you say missing not at random, you say, oh, missing at random, you say RY should be kind of independent from other things. No, according to the definition, RY is dependent on some variable that does not have missing values. And this is a missing not at random. Right here, you have missingness indicator for Y. This guy depends on W, and unfortunately, W may also have missing values. Okay, that's it. And this is a self-masking missingness. So whether my value is missing depends on my value, right? So you can think of a lot of scenarios where that's the case. And in single cell data, you can see if the gene expression level is very low, then it's more likely for the value to be 0, right? And at the same time, you may have dropout. So essentially, you can use this kind of thing to describe why the value is missing or why the value is 0 in the gene expression data scenario. In any case, we have a unified way to represent the relation among the variables and also between the variable missingness indicator and the variables. Good. Now you have a complete understanding of why things are missing and the relation among the measured variables and so on. Now you want to find the causal relationship. I will skip the assumptions. On the assumption, we can show something, but basically the message is very clear. First of all, those assumptions are relatively mild, very mild. And second of all, if you apply, say, PC to the data with missing entries, and you use the test-wise deletion strategy, basically you want to see whether X, Y independent given Z, right? As long as you have values for X, Y, Z, you use it. This is test-wise deletion, right? So you can have a graph because this way you can determine independence and conditional independent relations, and then you have a graph. Now you try to see how this graph is related to the underlying true graph. You want to see whether they are the same. If they are the same, you are very happy because even if you have missing entries, I can recover the truth asymptotically speaking. Is that right? Actually, there's only one situation. Only in one situation can you see some phenomenon, some issue with the discovery result by the test-wise deletion method. And basically, you can show the following thing. If X, Y are independent given Z in the test-wise deleted data, then there must be conditional independent in the original data. That's good. That means I can fully trust conditional independent relations discovered from the test-wise deleted data. Okay? And then if they are not independent, generally speaking, they are not independent in the original data without missing entries. But in one situation, that's not the case. In what situation? Do I have a figure here? Oh, no. Okay, let me just explain it. I might have deleted that slide. So you want to see whether X, Y independent given Z. Unfortunately, right here, they are always dependent. And the missingness indicator for those variables is, for instance, a common effect of the variables. Let me give an example, a single example, then you can see why this is the case you have to worry about. I want to see whether X, Y are independent given Z. Suppose in the original graph, they are independent. without this link, right? They are independent given Z. Good. Now, suppose actually R Z. Suppose this missing is indicator for Z is dependent on X and Y, determined by X and Y in a probabilistic way. Now, if you analyze the data with missing entries, you have to condition this guy. Because you cannot use the entries with missing values, right? You always condition this guy. And then unfortunately, since you condition this guy, there will be deconnected, right? So this is basically the only situation. Of course, if you have this, alternatively, if you have this, you have the same phenomenon. Okay. Because here, when you try to see whether X and Y are independent given anything, you always condition Rx. Because if X is missing, you cannot use the value, right? And then this is the descendant of the common we should go this way. This is the descendant of the collider. Then condition this guy, they will be deconnected. So basically, only in situations like this can you see extra dependence between X and Y. Good, that's the only situation. Of course, the next step is whether you can still do the correction. In fact, on the rather mild assumption, you can do correction. Essential idea that follows. I have, as you can see from here, I have missing this indicator depending on W, which is a common effect right here. And you can show that interestingly, because of a contribution from Mohan and Yuda Probe, you can recover the joint distribution of X, Y, Z from the missing data. Px, Y, Z, the original distribution, can be written this way by making use of W. You can do the correction. So you can recover the joint probability distribution in the original data by making use of the data set with missing entries, if this is the case. Okay, why can we do so? It's because Ry is conditionally independent from X, Y, Z given W. That's why we can introduce W here, and then we can remove W with the marginalization. You can recover the joint distribution. If you have a joint distribution, you can see whether X, Y are independent given Z. In this case, yes, X and Y are independent given Z. You know, there are no edge in between, right? So in theory, you can do it. Here you can see a kind of specific way to do that in the linear Gaussian case or discrete case. Okay, so to summarize, even if you have missing values, generally speaking, you can recover causal structure. And even if you use the naive method, you may just have very few extra links, right? Because of missing this indicator. And furthermore, in many cases, you can go further, you can do correction. Then you can recover the true causal graph from data with missing values. And I should stop here. And one thing, I will tomorrow morning, I will start with this problem of a causal discovery from non-stationary data. It's very quick. At least you can see how you can leverage from multiple distributions. And after that, you can see how we can recover latent variables and their relations. Okay, thank you very much, guys.